If I showed you Google Maps 50 years ago, you'd probably think I'm a heretic. Type in the address where you want to go and it shows you the exact route to take, building shapes, etc., and a map of the entire world in less than a second with no lag. Insanity! But it exists now and it's all free. So how does Google Maps even exist? The first step in making a Maps app is to get coordinates, latitude and longitude. Think of them as Earth's unique address system. Each point on the planet gets its address, forming a geodetic system. But flattening our round Earth onto a 2D map isn't straightforward. It's a bit like trying to flatten a beach ball without causing weird wrinkles. Enter the Mercator projection, which smooths things out but stretches land masses near the poles. With this method, Google Maps divides the world into a quadri grid system, slicing the map into tiles with unique IDs. Imagine a huge digital patchwork quilt where each tile can zoom in to reveal even more detail. So how does Google collect all this data? It's an all-terrain operation. Those Street View cars you see around, they're equipped with 9 high-resolution cameras capturing 360-degree views and LiDAR sensors shooting laser pulsars to map distances in 3D. In snow-covered regions, snowmobiles map the frosty paths. On rivers and canals, boats join the fleet. And in desert regions, even camels have cameras strapped on. If there's a place to map, Google's got a ride for it. But you probably knew all this, and this is just the beginning. How do we go from a Google car to a detailed map of the entire world? Capturing raw images is just step 1. Google then turns those images into something more meaningful, like arranging puzzle pieces on a recognizable picture. Here, photogrammetry does the heavy lifting, stitching billions of images into a cohesive 3D model of the world. Algorithms match common points across photos, a process known as structure from motion, to build spatial relationships. But what about those remote or restricted areas where no camera car or camel can roam? That's where satellites and aerial images come into play. High-resolution satellites provide sweeping overhead views, while drones offer close-up angles where satellites fall short, adding even more layers of detail. Machine learning then analyzes and categorizes all this data. Using convolutional neural networks, or CNNs, algorithms detect and classify features, roads, buildings, trees, and even rivers. And then there's semantic segmentation, where every pixel is labeled, giving context to each element. Imagine your map reading road signs or building names. Optical character recognition, or OCR, helps Google Maps do that. All these data types, vector for shapes and raster for textures, combine to create a rich, interactive world map. And just like that, with billions of snapshots and smart algorithms, we're handed a digital model of our planet, ready to explore. Once the world is digitally modeled, the focus shifts to enriching the map with precise, actionable details. Speaking of, thanks so much for all the support on the channel lately. It really means a lot, and I want to give something back to you guys. So do you need a job? That sounded a bit weird. But whether you're a UX designer, app developer, freelancer, or just a curious viewer, I want to get to know you guys, share some UX and UI tips, and maybe even get a gig. So I made a Discord channel for us and want to make this the place to be for front-end professionals. And I'm having talks with people to get some employers in there so you can connect with them too and find some jobs in the future. I'm really excited to get this thing started, so I hope you'll join me. Have you ever noticed how Google Maps goes beyond just showing roads? It's loaded with incredible detail, lane markings, trees, and even turn arrows. These high-definition maps, or HD maps, capture information down to the centimeter, which is essential for advanced navigation and especially autonomous vehicles. HD maps consist of several layers. First, the geometric layer details road shapes, width, and lane positions. Next, the semantic layer catalogs road signs, traffic signals, and lane markings, everything that helps define the rules of the road. Finally, the dynamic layer captures real-time changes like traffic conditions and temporary lane closures, constantly updating to stay accurate. But with so much data, how does Google Maps load so smoothly on your phone? The secret is vector tiles and smart data compression. Vector tiles use mathematical shapes, points, lines, polygons to represent features, making them highly lightweight and easy to transmit. Your device only requests the tiles it needs for the area you're viewing, so instead of overwhelming your bandwidth, it fetches data on demand. To avoid reloading the whole map with every movement, delta encoding is used, sending only changes from previous data. It's like having a map that loads as fast as you can scroll, data efficiency at its finest. At its core, Google Maps operates on a sophisticated microservices architecture utilizing containerized deployments managed by Kubernetes. The system processes 25 petabytes of data daily through a distributed computing framework. The vector tile system employs protocol buffers for efficient data serialization, while WebGL handles the rendering of 3D buildings and terrain with level of detail or LOD optimization. The routing engine utilizes a modified contraction hierarchies algorithm operating on a graph database with over 1 trillion edges. Real-time traffic updates are processed through Apache Kafka streams, with machine learning models running on TensorFlow, making predictions using historical and live data. The system maintains a 99.99% uptime through redundant data centers and edge caching, with response times averaging under 100 milliseconds globally. For data storage, Google Maps combines Bigtable for real-time data access and Cloud Spanner for globally consistent transactions, while using protocol buffers for efficient data serialization and transmission. The system is orchestrated through a sophisticated service mesh that handles load balancing, circuit breaking, and fault tolerance, ensuring seamless operation across multiple geographic regions. While ground-level data provides incredible detail, the true power of modern mapping comes from above. Did you know that Google Maps has a literal bird's-eye view? Satellites orbiting high above Earth capture massive views with astounding precision, even in invisible wavelengths. Using multispectral imaging, satellites can collect data in various wavelengths, showing everything from vegetation health to water bodies. For even greater detail, satellites use synthetic aperture radar, or SAR, which sends microwave pulses and measures their return times. SAR can see through clouds, rain, or fog, providing images even during bad weather or at night. After collecting the data, orthorectification corrects any distortions from Earth's terrain, aligning each pixel to a precise location for a perfect fit on our maps. But satellites do more than just snap pictures. They're the backbone of global navigation. The US operates the GPS constellation with 31 active satellites, while other systems like China's Beidou, Europe's Galileo, and Russia's GLONASS contribute to global positioning. Regional systems, such as India's Navik, improve accuracy in specific areas. Each satellite transmits signals with precise timestamps, allowing devices to calculate their exact location based on the time it takes for those signals to travel, triangulating your position within meters. And how does all this technology translate into seamless navigation for your device? Let's explore the GPS mechanics and see how real-time data brings the map to life. Have you ever wondered how your phone knows your exact location? GPS satellites allow the cars to have an invisible guide over the signals sent in light years. The device listens for signals from a minimum of 4 satellites, and cross-referencing the precise time the signals were sent and received will determine the distance to each satellite. Trilateration describes this process in which distances are used to identify your exact coordinates. That said, as always, the city has its own set of hurdles. Towers may not be in the line of sight and can reflect or block signals. Both cause multipath errors. This is where assisted GPS, or AGPS, comes along and saves the day. Using cell towers and Wi-Fi data in AGPS provides better accuracy and helps lower the time taken to find the location. It's as if you have some clarity in difficult places, helping you stay on the right path. Then you factor in real-time data. Anonymized location and speed data from millions of devices feed Google's traffic models. Data fusion combines inputs from the many sensors and cameras and historical traffic flow patterns. At the same time, machine learning algorithms analyze the information to predict traffic flow and estimated travel times while recommending alternative routes. Dynamic rerouting uses this information to modify your route in real time, responding to incidents, traffic jams, and other unexpected events that may happen along the way, such as minimizing the impact of an accident or a road closure. View it as your traffic analyst, keeping you out of traffic jams before they occur. So now that we're navigating smoothly, we gotta figure out how much time it takes to get there. Have you ever wondered why Google Maps offers different routes depending on your mode of transportation? It's all about tailoring the journey. For drivers, routing algorithms factor in speed limits, road types, and real-time traffic conditions. Complex algorithms like Dijkstra's and A-star, find the shortest or quickest paths, balancing safety and efficiency. On the other hand, walkers get routes through pedestrian paths, parks, and shortcuts, avoiding highways. Elevation data helps detect steep inclines, ensuring you don't go on a hiking expedition when you just want to stroll. Bikers benefit from routes along bike lanes, quieter streets, and paths with fewer hills. These bike-friendly paths use elevation and surface-type data, favoring paved roads over gravel paths. Google Maps algorithms use cost functions to weigh factors like time, distance, and energy consumption, key for bikers. Multi-objective optimization allows for these balanced, customized suggestions. Machine learning also makes your experience more personal. If you tend to avoid highways or prefer scenic routes, Google remembers. Emerging technologies, like autonomous vehicles, rely heavily on these high-definition maps, with lane-level precision critical for safe navigation. But Google Maps is more than just algorithms and data. It's a cultural map, too, adapting to political boundaries and local laws. Curious how that works? Let's dive into the geopolitics of mapping. Boundaries and borders aren't universally agreed upon, so Google customizes maps based on local laws and cultural nuances. For instance, a border shown in one country might look entirely different in another. Certain map details might even be blurred or omitted in some regions to comply with regulations. And it's not just about displaying boundaries. Some conflict zones see GPS signal interference. In areas of high tension, signals can be jammed or even spoofed to send misleading data, complicating everyday navigation and aviation and maritime operations. Navigation systems rely on error detection and correction to manage these challenges, but it's a constant game of technological chess. Maintaining the integrity of map data requires rigorous verification. Google cross-references authoritative sources to ensure accuracy, while clever trap streets, invented streets used as a watermark, help detect unauthorized copying. Community contributions also play a role. Local guides frequently update places and reviews, and machine learning validates the data to keep everything fresh. Privacy laws like GDPR in Europe set strict standards for data handling. Google anonymizes data to protect user identity while still providing valuable traffic information. It's an intricate dance where technology meets geopolitics, yet all you see on your phone is a seamless map. Isn't it remarkable how these layers work together? So with all the data, boundaries, and algorithms in place, what does it all add up to? Well, nothing if you can't search up Google Maps on Google in the first place. So how does Google itself exist? Click here to find out, and I'll see you next time.